Deep within the vast expanse of the Milky Way galaxy, amidst billions of stars, lies a question that has captivated human imagination for centuries. Are there other planets like Earth? In the grand tapestry of the cosmos, we are but a tiny thread. Our home, Earth, is just one planet orbiting one star among billions in our galaxy. Yet, as we gaze into the night sky, we can't help but wonder if there are other worlds out there, like our own, teeming with life. This curiosity fuels our relentless pursuit of knowledge, leading us to the enigma of exoplanets. Exoplanets are planets that orbit stars other than our Sun. They are celestial bodies scattered across the universe, each with its own unique story to tell. Since the first exoplanet was discovered in 1995, our understanding of the universe has been turned on its head. Thousands of these distant worlds have been detected, each more intriguing than the last. Gas giants larger than Jupiter, rocky worlds scorched by their stars, icy planets in the far reaches of their systems. The diversity is mind-boggling. Yet, in this cosmic sea of possibilities, our search is focused on finding an exoplanet that resembles Earth, a world with the right conditions to potentially harbor life as we know it. But how do we find such a world among the billions of stars in our galaxy? The challenges are immense. Not only must the exoplanet be the right size and composition, but it must also orbit its star at just the right distance. Not too close, not too far, where the conditions might be just right for liquid water to exist. It's a delicate balance, and the task of finding such a world is akin to searching for a needle in a haystack. Yet, despite these astronomical odds, our search continues, driven by our innate curiosity and thirst for discovery. We've discovered thousands of exoplanets so far, but finding one that resembles Earth is like searching for a needle in a haystack. Who knows, perhaps the next distant world we discover will be the one that finally answers the age-old question, are we alone in the universe? Scientists use ingenious methods to detect exoplanets, such as measuring the dimming of a star as a planet passes in front of it, or observing the wobble of a star caused by the gravitational pull of an orbiting planet. These techniques might sound like something out of a science fiction novel, but they're the backbone of our search for Earth-like planets in the Milky Way galaxy. The first technique, known as the transit method, is a bit like watching a fly pass in front of a light bulb. When an exoplanet orbits in front of its star, it blocks a tiny fraction of the star's light, causing it to dim slightly. By observing these minute changes in brightness, scientists can deduce the presence of an orbiting planet. They can even determine the planet's size and orbit from this data. The second technique, called radial velocity, is all about the wobble. Just as the Earth's gravity tugs on the Moon, causing it to orbit around us, a planet's gravity also tugs on its star. This tug-of-war causes the star to wobble slightly. By observing this wobble, scientists can infer the presence, mass, and orbit of an unseen planet. These two methods have been incredibly successful in detecting exoplanets. In fact, they've led to the discovery of thousands of these celestial bodies, each one a potential clue in our quest to find another Earth. But let's not get ahead of ourselves. While the discovery of any exoplanet is a triumph, not all of them are candidates for being Earth's twin. Many are gas giants like Jupiter, while others are too hot or too cold to sustain life as we know it. Only a select few reside in the Goldilocks zone, the region around a star where conditions are just right for liquid water to exist. These are the planets that truly pique our interest. These are the worlds that could potentially harbor conditions similar to Earth. While many exoplanets have been discovered, only a handful are considered potentially Earth-like. And so, the search continues as we cast our gaze to the stars, ever hopeful of finding another place in the universe that we can call home. These planets reside in what scientists call the habitable zone, the region around a star where conditions may be right for liquid water to exist. You can think of the habitable zone as the Goldilocks zone of a solar system. It's not too hot, not too cold, but just right for water to remain in liquid form on a planet's surface. And where there's water, there's the potential for life as we know it. This zone is crucial in the hunt for Earth-like planets. It's a delicate balance, too close to the star, and any water would evaporate in the intense heat. Too far away and the water would freeze in the icy cold. The habitable zone is that sweet spot where a planet could have liquid water and potentially life. But it's not just about distance. The size of the planet and the type of star it orbits also play a significant role. A larger planet might have a thicker atmosphere that can trap heat, while a smaller star might have a closer habitable zone. One exoplanet that has sparked interest is Kepler 186f. This planet, discovered in 2014, is located in the constellation Cygnus, about 500 light-years from Earth. Kepler 186f is particularly exciting because it's roughly the same size as Earth and is located in the habitable zone of its star. This means it has the potential to hold liquid water on its surface, much like our home planet. But there's a lot we still don't know about Kepler 186f. We don't know if it has an atmosphere, and if it does, what it's made of. We don't know if it has water, and if it does, whether that water is in liquid form. Still, the possibility is tantalizing and continues to drive our search for life beyond Earth. One such exoplanet is Kepler 186f, located about 500 light-years away. It's similar in size to Earth and orbits within the habitable zone of its star, raising hopes that it could have liquid water on its surface. Studying the atmospheres of exoplanets is crucial in determining their potential habitability. The atmosphere of a planet is like a fingerprint, unique and telling. Every gas molecule, every trace element, tells a story about the planet's history and its present state. By analyzing these atmospheric fingerprints, we can piece together a comprehensive picture of an exoplanet's environment. Consider our own blue planet. Earth's atmosphere is a cocktail of nitrogen, oxygen, and trace amounts of other gases, a unique mix that supports life as we know it. It's this balance of gases that keeps our planet warm enough to support liquid water, a key ingredient for life. Now imagine we could detect a similar atmospheric composition on an exoplanet. That would be a strong indicator that the planet could potentially support life. Of course, it's not as simple as finding an Earth clone. Life, as we're coming to understand, might not be limited to conditions exactly like ours. Scientists have been using telescopes to analyze the light that passes through an exoplanet's atmosphere. This technique, known as spectroscopy, can reveal the presence of various gases. Oxygen, for instance, could hint at biological activity. Meanwhile, gases like carbon dioxide could indicate a greenhouse effect, potentially warming the planet enough for liquid water. The challenge, of course, is that these signals are incredibly faint and often obscured by other cosmic noise. But with each technological advancement, we're getting better at picking out these signals from the cosmic symphony. Future telescopes promise even greater sensitivity, opening up new possibilities for atmospheric analysis. The search for life beyond Earth is a puzzle of cosmic proportions. Each exoplanet we study adds another piece to that puzzle. By studying their atmospheres, we're not only learning about these distant worlds, but also about the potential for life in the universe. By analyzing the composition of gases surrounding these distant worlds, scientists can glean valuable insights into their suitability for life. This is the tantalizing promise of exoplanet atmospheric analysis, a field that is just beginning to come into its own. Future space missions, such as the James Webb Space Telescope and the upcoming LUVOIR and HABEX missions, promise to revolutionize our understanding of exoplanets and potentially discover more Earth-like worlds. These space telescopes, designed with cutting-edge technology, will observe the cosmos with unprecedented detail and sensitivity. The James Webb Space Telescope, set to succeed the Hubble, is equipped with a mirror nearly 3 times the size of its predecessor, enabling it to capture sharper images of distant celestial bodies. This giant leap in observational power will allow astronomers to peer back into the early universe and detect faint signals from far-off exoplanets. The LUVOIR mission, short for Large Ultraviolet Optical Infrared Surveyor, is another ambitious project on the horizon. This space telescope, still in its conceptual phase, promises to dwarf even the James Webb in terms of size and capability. It aims to directly image Earth-like exoplanets, a feat never achieved before, and decipher the chemical makeup of their atmospheres. Similarly, the HABEX, or Habitable Exoplanet Imaging Mission, is being designed with a primary goal of finding Earth-like exoplanets in habitable zones. Its advanced instruments will scrutinize the atmospheres of these exoplanets for signs of life, such as oxygen, water vapor, and methane. The potential of these missions is immense. They could transform our understanding of the universe, unveiling secrets from distant worlds that we can currently only speculate about. More than that, they might provide answers to the age-old question of whether we are alone in the universe. As we continue to peer into the depths of space, the search for another planet like Earth in the Milky Way galaxy remains one of the greatest scientific endeavors of our time. Who knows what wonders await us in the vast cosmos?